GeForce RTX 5090. Over 1,000 components, hundreds of manufacturing stages, shipped to gaming systems worldwide.
Inside this advanced TSMC facility, RTX 5090 GPUs are patterned on 300mm silicon wafers every hour. Today, we follow RTX 5090 from raw silicon to finished graphics cards, revealing each hidden manufacturing stage. In tightly controlled cleanrooms, every wafer's journey is tracked, timed, and logged for complete production traceability.
Engineers supervise thousands of parameters, tuning recipes so Blackwell wafers meet strict yield and performance targets.
Automated vehicles move wafers between stages, reducing handling, contamination risk, and time lost in internal logistics.
Completed RTX 5090 cards leave in tightly scheduled batches, feeding global supply chains for PC builders and gamers. Behind every RTX 5090 lies a vast ecosystem of materials, tools, and expertise synchronized into one seamless process.
Every input, from silicon wafers to chemicals, arrives documented, sealed, and verified before it enters the clean manufacturing environment. Incoming wafer lots undergo visual and handling checks, ensuring no damage before precise processing even begins.
Computerized storage manages wafer inventory, sequencing lots so each enters production at the ideal time and condition.
Strict gowning and air shower protocols protect wafers, keeping airborne particles far below critical defect thresholds. Bare wafers transfer into sealed pods, isolating them from the room and enabling ultra-clean automated handling. Before any circuitry is built, wafers are repeatedly cleaned with ultra-pure chemistries to remove microscopic contaminants.
High-temperature furnaces grow nanometer-thin oxide layers, forming the electrical foundation for future transistor structures.
Chemical-mechanical polishing flattens wafers, ensuring later layers stack evenly and maintain pattern fidelity across the surface.
Metrology tools measure film thickness and uniformity, providing immediate feedback to keep early process steps in control.
Material flows, wafers, gases, chemicals are segregated, tracked, and verified, forming the foundation of reliable GPU fabrication.
Photoresist is spun onto wafers, forming a uniform light-sensitive layer only hundreds of nanometers thick. Soft bake ovens remove solvent and stabilize the resist layer, preparing it for precise pattern exposure.
Automated tracks align each wafer with sub-micron accuracy, ensuring future layers stack perfectly across the die.
Lithography exposes Blackwell's intricate patterns, shrinking mask designs onto wafers with nanometer-scale precision.
Developer Solution washes away targeted resist regions, revealing a patterned mask that will guide silicon etching.
Active plasmas etch exposed areas, transferring the resist pattern into underlying layers that form device structures. Resist removal and cleaning leave precisely etched patterns, the first structural features of the future RTX 5090 GPU.
Atomic layer and chemical vapor deposition lay conformal films, enabling precise stacks for advanced transistors. Ion implantation sets dopant profiles with exact energy, angle, and dose to tune transistor behavior.
Rapid annealing repairs implant damage and activates dopants, locking electrical characteristics into silicon.
Shallow trench isolation defines device boundaries, insulating transistors to maintain signal integrity at scale.
Lithography and etch sculpt nanoscale fins, creating channels that enable modern high-performance logic. High-K dielectric layers boost gate capacitance while suppressing leakage, enhancing transistor efficiency. Metal gates pair with high-K dielectrics, using gate-last integration to preserve material integrity. Sidewall spacers set implantation boundaries, reducing fields and improving device longevity and performance.
Epitaxy and silicidation create low-resistance paths, enabling fast switching and efficient power delivery.
Pre-metal dielectrics insulate devices and prepare surfaces, ensuring precise contacts and interconnects later. Contact etch and tungsten fill create robust connections from transistors to the wiring stack. Back-end begins with low-K dielectrics and patterned roots, minimizing capacitance for faster signaling.
Dual Damascene etches vias and trenches, preparing a single copper fill to form interconnects.
Barrier and seed layers precede copper electroplating, ensuring adhesion and uniform, void-free metal fill. Chemical-mechanical planarization levels copper, leaving clean inlaid interconnects ready for next layers.
Layer by layer, stacked interconnects scale signals vertically, forming complex multi-level wiring networks.
CDSEM and overlay metrology maintain line widths and alignment, safeguarding pattern fidelity. Automated inspections catch defects early, feeding SPC systems that protect yield and uptime.
Low-K dielectrics reduce parasitic capacitance, cutting RC delay for higher interconnect performance.
Electromigration tests validate copper reliability, shaping liners and processes for long-term stability. Gate-last integration preserves high-K integrity, avoiding damage from earlier high-temperature steps. Tilted implants shape junctions precisely, with dose control ensuring uniform electrical characteristics.
Frequent cleans remove residues and particles, protecting subsequent patterning and interconnect quality.
Inline electrical tests validate device and wiring health, catching drifts before full wafer completion. Top passivation seals the stack. Completed wafers await dicing, packaging, and further testing.
Wafer probing screens every Blackwell die electrically, mapping performance bins before any costly packaging begins. Test data guides yield improvement, while software maps defective dies to avoid packaging non-functional GPUs.
Dicing saws cut wafers into individual RTX 5090 dies, controlling chipping and protecting fragile structures.
Sorted dies are gently transferred to trays, preserving integrity while maintaining full traceability back to each wafer. Die-attach tools mount GPU dies onto substrates with micron precision, forming the foundation of each package. Controlled thermal profiles cure die-attach materials, securing each GPU die mechanically and thermally to its substrate.
Underfill epoxy flows beneath the GPU die, strengthening microscopic joints against thermal and mechanical stress. Flip chip bonding creates dense arrays of bumps, providing high bandwidth, low resistance paths between GPU and substrate.
Epoxy molding encapsulates GPU assemblies, shielding dies and interconnects from moisture and mechanical damage.
Triangulation separates molded panels into individual GPU packages, each sized and finished for board-level mounting. Laser marking encodes every RTX 5090 package with unique IDs, enabling complete lifecycle traceability.
Package-level testing validates GPU functionality, performance, and power behavior before any device reaches a graphics card.
Burn-in stress exposes early life failures, ensuring only robust RTX 5090 packages progress to system integration. Final outgoing checks combine dimensional, cosmetic, and electrical controls, tightening quality gates at the package level. Tested GPU packages move into controlled storage, queued precisely for graphics card PCB assembly lines. Multi-layer GPU PCBs arrive from dedicated board fabs, inspected and staged for automated surface mount assembly. Solder paste printers deposit controlled volumes on each pad, forming the future solder joints for every component. 3D paste inspection verifies volume and alignment, catching printing defects before components ever touch the board. Pick-and-place machines populate support components at high speed, guided by CAD data and vision alignment.
The RTX 5090 GPU package is placed with extreme care, its dense BGA aligned to every board pad.
Controlled reflow profiles create strong solder joints, simultaneously connecting every component and GPU to the PCB.
AOI systems scan each assembled board, detecting errors that escaped programmatic checks or placement safeguards.
X-ray inspection reveals hidden BGA joints under the GPU, verifying solder integrity where cameras cannot see.
Through-hole elements and connectors join via selective soldering, complementing SMT to finalize board connectivity.
Initial board-level tests validate that each RTX 5090 card powers up, enumerates, and runs key workloads correctly. Heat sinks and thermal pads mount with controlled force, ensuring efficient heat transfer from GPU and memory.
Triple fan modules are verified for speed, noise, and current before joining the RTX 5090 cooling assembly.
Shrouds and branding complete the card's exterior, combining thermal design with industrial aesthetics.
Rigid backplates reinforce the PCB and aid cooling, protecting RTX 5090 cards during installation and transport.
Firmware programmers load and verify RTX 5090 VBOS, standardizing behavior across thousands of graphics cards.
System-level tests push graphics, compute, and memory, binning RTX 5090 cards by stable performance margins. Thermal profiling confirms cooling performance, ensuring RTX 5090 temperatures remain within design margins under full load. Power testing validates draw and transients, aligning RTX 5090 behavior with specified limits and PSU guidelines.
Mechanical checks stress connectors, confirming reliable insertion, retention, and electrical contact for repeated user handling.
EMC and ESD tests ensure RTX 5090 cards integrate cleanly into systems while meeting global regulatory standards.
Dimensional inspections confirm form factor compliance, ensuring RTX 5090 fits cases, slots, and cooling clearances correctly.
Noise tests characterize acoustic signatures, tuning cooling profiles so RTX 5090 balances thermals with user comfort.
Extended burn-in exposes marginal components, filtering out early failures before cards enter distribution channels.
Failure analysis closes the loop, turning rare defects into design and process improvements for future builds.
Cosmetic inspections protect brand perception, ensuring RTX 5090 ships free of visible defects or print flaws.
See the misprint right here.
Yeah, definitely flagged.
Automated labeling ties each RTX 5090 to digital records, enabling tracking from factory to end user. Automated box lines form protective retail packaging, ready to cradle each RTX 5090 card securely. ESD-safe bags and desiccants guard electronics from static and moisture during storage and shipping. Inserts position RTX 5090 securely, while sealed boxes and checkweighers verify every package is complete.
External codes group boxes by lot and destination, streamlining traceability across the distribution chain.
Palletizers and stretch wraps secure shipments, preparing RTX 5090 loads for international freight routes.
Automated storage keeps RTX 5090 inventory organized, traceable, and ready for just-in-time carrier pickups. At the dock, pallets are scanned onto outbound trucks, linking every shipment to digital manifests and routes. Logistics teams orchestrate global flows, balancing speed, cost, and emissions for RTX 5090 deliveries.
From sand to silicon to system, RTX 5090 embodies a global collaboration of fabs, factories, and engineering.
Behind each wafer tool, optimized utilities reclaim heat and cut energy per processed RTX 5090 die.
Ultra-pure water plants feed the fab, recycling, and polishing water to meet strict semiconductor-grade purity. Advanced treatment systems recycle the majority of process water, reducing fresh withdrawal and discharge volumes.
On-site renewables and green procurement cut the carbon footprint of each RTX 5090 wafer processed.
Closed-loop chemical systems prevent leaks and track usage, minimizing waste and environmental risk.
Scrubber systems neutralize process gases, keeping emissions from advanced wafer tools within strict environmental limits.
In-plant recycling programs recover cardboard, plastics, and metals, diverting large fractions of waste from landfills.
Teams evaluate footprints per GPU, setting tighter energy, water, and waste targets with each product generation.
Upstream PCB suppliers implement copper recovery and water reuse, shrinking the extended RTX 5090 supply footprint.
Optimized logistics favor efficient modes, lowering emissions associated with moving RTX 5090 worldwide. Return centers repair and refurbish usable cards, extending hardware life and reducing demand for new production.
End-of-life GPUs are shredded and separated, recovering metals and components instead of sending boards to landfill.
Regular lab analyses confirm treatment performance, driving continuous reductions in hazardous outputs per GPU produced. Staff training embeds sustainability into daily work, aligning operator decisions with environmental goals. Digital traceability links each RTX 5090 to its full manufacturing history, supporting recalls, audits, and lifecycle analysis. Supply chain teams balance cost, risk, and ESG scores, shifting toward lower impact, more resilient material sources.
Emergency drills and automated safeguards prepare fabs to handle incidents quickly with minimal environmental impact. Design reviews explore ways to reduce materials and improve recyclability in future RTX architectures.
Public sustainability reporting tracks progress, holding manufacturers accountable for reducing impacts while scaling performance. Structured training centers shorten learning curves, transferring deep fab knowledge to the next generation of engineers.
Apprenticeship programs develop technicians locally, building long-term semiconductor talent pipelines around advanced fabs.
AI models watch thousands of signals, predicting excursions early so engineers correct issues before yield suffers.
Automated material handling moves wafers precisely, cutting contamination, human travel, and idle time between process steps. Autonomous mobile robots extend automation into tight spaces, flexibly supplementing fixed transport rails. Digital twins model the factory virtually, testing layout and recipe changes without risking live production lots. Kaizen workshops enlist operators and engineers to remove waste, raising throughput and quality incrementally.
Predictive maintenance uses sensor data to service tools just in time, maximizing uptime and process stability.
Daily operations reviews align safety, quality, delivery, and sustainability targets around every RTX 5090 lot produced.
Joint design teams balance performance with manufacturability and recyclability for the next wave of RTX GPUs. Global coordination synchronizes capacity and risk management, keeping RTX 5090 supply stable despite shifting conditions.
AI-augmented robots handle repetitive tasks, freeing human experts to focus on complex optimization and problem-solving.
Immersive training and AI tutors preserve expert knowledge, standardizing best practices across growing fab teams.
Regular safety drills protect people and tools, reinforcing disciplined responses in high-stakes manufacturing environments.
R&D labs proved new architectures and processes long before mass production, de-risking each RTX generation's ramp.
Decades of accumulated expertise underpin every process recipe, bridging foundational physics with today's extreme scales.
Behind RTX 5090 stands a global community of specialists, each contributing a link in the manufacturing chain. Around the clock, fabs run continuously, translating designs into silicon to meet relentless global demand. Each RTX 5090 connects invisible factories to visible creativity, research, and entertainment in everyday life. From raw silicon to global desktops, RTX 5090 showcase modern manufacturing